Here we go. So, we started our unit talking about different types of properties, and one of the properties, or one of the types that we talked about, was physical properties. And physical properties can be broken down into extensive and intensive properties. So extensive properties depends on the amount of material, or how much material or matter, mass, how much stuff is there. Okay. Intensive, it doesn't matter. So extensive properties depend on how much stuff you've got there. So I'm going to kind of do a T-chart here. What's the difference? Extensive is going to be, depends on the amount of material you have. And this is, it doesn't depend on how much. Extensive, you could have like volume, mass, amount of energy, weight would be another one here. So those are all examples here. Intensive would be like boiling point. It doesn't matter how much you have, it's going to boil at the same temperature. It may take more energy to get a sample to boil, but the boiling point, the temperature that happens at, is going to be the same. Density, melting point or melting temperature. Temperature itself. Okay. Now, amount of energy is different from that, remember. Okay. If you take physics, you'll end up getting a good dose of that in there. All right, then we have some kind of basic definitions. So your atom is going to be the smallest unit of matter. That maintains its chemical identity. Okay. Let me see. Let me put up my answer key for some of this. Make it go a little bit faster for you guys. And then when we get into ones where I need to actually show you how to do stuff, we can. So compound, substance made of 2 or more atoms that are chemically bonded, can't be broken down into simpler, stable substances. If you break it down, you break it down into elements, okay? So you can't get further down. So you got atoms, and then atoms make up compounds, and then atoms and compounds will make up your mixtures. Mass then is the amount of matter in a substance. And then we asked you for examples of matter and examples of non-matter. So examples of matter would be like air, smoke, water vapor. Examples of non-matter would be like light or radio waves, any forms of energy like that. Chemical change then, change that always changes the identity of a substance. So examples of that would be like burning, leaves changing color, rusting. Those would be examples. And then physical changes are changes that do not change the identity of substance. So condensation, melting, grinding, cutting, boiling. Boiling is a phase change. All phase changes are physical changes. Minerals dissolved in water, like salt water. Salt from evaporated water. Those would be physical changes. We talked about noble gases. Those are atoms that don't react. They're on the last table of the periodic table. And why they're called noble is because like the nobility don't interact with like common people. Like they're too good for us. I think they do come out and talk to the masses once in a while and shake hands and everything, but you know. All right, any questions on page 1? I believe it's page 1. Yes, ma'am. Yeah, just leave your phone with Fernando or intake Fernando, okay? Isn't that funny? I thought of jerseys. I thought of football jerseys, and you got like a soccer one on, and she's got basketball. That's kind of cool, you know, like broaden my perspective of things. Jersey day. All right. The next one was completing a table. So if we have a solid form, solid, the shape is going to be definite. The volume is going to be definite. Liquid, you've got variable shape. It's going to take the shape of its container, but it has a definite volume. We can use like a graduated cylinder like we did back in our last chapter to figure out the volume of it. Gas, though, is going to be variable on both fronts. So it takes the shape and volume of whatever container it's within. All right. What happens to the energy as energy changes state? It's going to change forms, but it's not going to be created or destroyed. So you can't, just like matter, you can't create or destroy energy under normal circumstances. There's nuclear stuff that can do that, but that doesn't happen kind of on a normal basis in our where we're at. Obviously, it happens on the sun. We can see the sun, but and it'll happen in like nuclear power plants. Hopefully, not nuclear bombs, but you know. All right, the diagrams I promise you on the test are a little bit easier to follow than these. So this is going to be, you could argue a homogeneous mixture. I almost kind of like this one labeled as heterogeneous because it's separated out onto 2 phases or 2 layers, which is pretty typical of a suspension. So you could argue either homogeneous because of particle size, or you could argue heterogeneous because of the suspension idea where it's in 2 different layers. Here, this one's definitely heterogeneous. You've got lots of differently sized particles in here. Homogeneous and mixed thoroughly throughout, so that's definitely homogeneous. And then this would just be an element because it's only one thing in there. All right, we also had some examples in your notes that you can go back to and kind of look those over. So you will have diagrams like this that you have to identify on the test. Homogeneous mixtures are also called solutions. We have periods on the periodic table, and those are called, rows are called the periods, and then groups are your columns. They're also called families sometimes. And they do have things in common, and as we get into chapter, I believe it's chapter 6, we learn why that's the case. All right, characteristics of metals. We've got good conductors of heat and electricity. They're ductile. Ductile means that they can be pulled out into thin wires. They're malleable, which means that they can be pounded into thin sheets. Your nonmetals then end up being brittle and hard. Metalloids are also called semiconductors. All right. Then the mathy parts, I want to spend a minute going through some of those with you so that it's a little bit easier for you to see how I came up with my answers on that. All right, so we've got, remember that by nature of the conservation of mass law, whatever we start with, we have to end with. So if we have 9 grams of A and 18 grams of B, what would it be when it combined together? Well, all we have to do is add those together. So that would be 27.0 grams of AB. And actually, I shouldn't have my 0 here. Okay, so if we're keeping with sig figs, this is to the singles place. This was to the tenths. So my answer should be to the singles at the least. Okay, so if we're looking at sig figs, that's how that works. All right, here we're looking at ratios. If we have CuO and it is 26.4 to 19, if we take that and increase the oxygen and double the oxygen, how many grams of oxygen will we end up having? 38. All right, makes sense? Okay, so then back to here, we've got pure substances. They're substances with fixed ratios and definite properties. We have 2 categories of pure substances, compounds and elements. And then here are some kind of listings of pure substances. And for elements, you'll have your periodic table, so you'll have 118 to choose from for elements, okay? Brass, I don't know if brass really belongs. Yeah. It's kind of a mixture. I wouldn't really call that a compound. I would take that off. I don't think I can. I'm going to take that off. Edit text images. I think it's going to let me take it off. If I take it off, I have to take, no, it is. Oh, cool. That's slick. There we go. All right. Mixtures then, physical combining of 2 or more substances, but they're physically combined. So we can use physical means to separate them. 2 different types of classifications then. We have homogeneous and heterogeneous, and then they wanted us to give examples of those. We've got solutions, vinegar, stainless steel, salt water, and then for heterogeneous, like wild bird seed, orange juice with pulp. Anything that says shake before using, that's going to be heterogeneous. Does heating always cause a chemical change? No. You heated, for example, that wire in lab, okay? That just made it glow, and then it cooled back down. Your regular light bulbs, like not the LEDs and not these fluorescent ones, but the original light bulbs where they had the wire inside and they would burn out pretty easily, and they have them, they call them like Edison light bulbs now. There's actually a wire in there, and what it does is it just glows. Okay, it doesn't burn, it just glows, and then you turn the light off and it stops glowing. It's still a wire, it didn't change it. Okay, but that light bulb gets hot, doesn't it? Have you ever touched the thing? Yeah, it gets hot in there. Copper, and so like I said, and then the wire that you used, but sometimes it'll cause a physical change. It'll glow, it'll boil, it'll melt. But sometimes it does cause a chemical change. Just depends. Okay? The magnesium that you had in lab in the little, when you did your percent mass example, that. Okay. So let me switch back over here so we can do some more math. All right, so we've got different samples here. They want to know what the percent mass is. And on yours, on your test, I have these all at the same place values, so it'll make it easier as far as sig figs is concerned. All right, so we've got 9.63 is our sample mass. We've got 1.93 divided by 9.63, and that's 20% then. Okay, so if this is 20% and there's only two components, what does that mean that this is? 80%. And you could run the math if you wanted to. You could take this and divide by this, but if you can, that's a little bit faster, I think. If there's two components, you can do that. If there's more than two, then you can't do that at that point. All right, the next one, we've got 71.71, and we have 95.62, and this one ends up being 75%. So if this is 75%, that means that this is 25%. This is 12.5%. So that means that this is 87.5%. And this is 80%, which means, oops, I should keep this to the tenths place. This is 20%. Okay. So how did I get these numbers? Well, I did part divided by the whole. So 20 divided by 25, 20.4 divided by 25.5 gave me my 80. 5 divided by 40 gave me this. 71.71 divided by that gave me 75%. And 1.93 divided by 9.63 gave me 20%. And then, like I said, I just subtracted these values from 100 to get these. Any questions on how to do that? All right. They were asking here, so what is the ratio of A to B in each sample? So we did that over here. What do these percent mass, how do they compare? Are any of these the same? No. So no samples have the same percentage. Okay, so what can we conclude about the samples? They are not the same substances. Assuming that the chemist was looking for a compound that was 20% A and 80% B, how would they determine if they had found that compound? They would compare the percent masses, and they would be able to see that sample 1 was the one that he was able to find. So compare percent mass and see if any match. Compound 1 matched. Questions? All right, and then here's some more. So we did 28. He found it. We talked about that. All right, so the next one is we're taking this we have this many grams of this, and we have this many grams of this, and we're forming this guy. So if we have our reactants here, how do we figure out how many products we made? Conservation of mass law. Yeah, we just add them together. Okay? Because conservation of mass says that, yep, we didn't create anything new. All right, so 80.5. And so that's 154.84 grams of ZnF2. All right, here we've got 14 combining with 97. They're asking how many grams form with this one. So 14, 97. I ended up with 111 grams of XY. So this is one of those ratio ones. If we have, no. Yeah. So if we have 95 grams and 8 grams going into XY, they want to know if we created XY2, how many grams of Y we would need. So that would be 16. Because we would end up needing twice as much. So this is a ratio problem here, okay? If this to this is X to Y, then if we doubled Y, how many Y would we need? All right, then we've got this guy. So if I had, if I said that I had 100 students at Craig and 25% of those are freshmen, how would I figure out how many freshmen I have? What math would I do to figure this out? Yeah. How do I do that? How do I know what 75% of this is? How do I know what 25% of this is? How do I calculate that mathematically? I'm guessing you guys can do this one in your head, right? But how do you do that? What if I said that there were 200 kids at Craig and 25% of them are freshmen? How would you figure that out mathematically? What would you do? Yeah.
Add by 4.
Well, you could, but okay, then let's make it a little harder. Let's say that 37.5% are underclassmen and we've got 200 kids. How would I figure that out? Yeah. Yep, you can do that. So 200 divided by 100 times 37.5, that would get it going, okay? I typically like to think of it this way, though. I'm going to divide this by 100 instead of dividing that, okay? Because this is in percent form, and if I want to get it out of percent form, I'm going to divide it by 100, not this first number, okay? Does that make sense? So if we are trying to figure out this problem, we're going to use the same methodology. We've got 297 grams. We're going to multiply that by 7, and then we're going to divide that 7 by 100 to get that out of percent form. Okay? And when we do that, it ends up being 200 and... Nope. 297 times is 20.79. That is my grams of oxygen. They didn't ask me about grams of oxygen. They asked me about grams of mercury. So now I need to take this and I need to subtract it. And when I do that, if I keep with sig figs, it's 276 grams of mercury. Make sense mathematically? All right, then we do a percent mass here for the following elements. We've got to take an inventory. How many nitrogen do I have? I have to distribute through my parentheses. How many nitrogen? 3. How many hydrogen? 12. Phosphorus is 1 and oxygen is 4. Then we go to our periodic tables and we find the mass off the periodic table for this guy. And we're going to round those masses to the 10th place. Then we multiply them out. So I've got 14 times 3. And that is 42. Okay, so those are my parts. How do I get my whole? Add them together. So I got 149 when I added those together. So I'm going to divide each thing by 149. And then I'm going to multiply by 100. I'm going to go to the 10th place for my answer, and my units are going to be percent and whatever element I am is my part. So this ends up being 28.2. This one ends up being 8.1. You end up with 20.8. And 43. One way round. All right, so then I add these up. I'm going to just do a verification to make sure that these came out right. So 8.1, 20.8, and 43. They should add up to be 100. They added up to be 100.1. But because of rounding, sometimes you'll end up with 100.1. Sometimes you'll end up with 99.9. You get anywhere on the other side of these, though, and you probably goofed something. So go back and check your work. Okay, but you will occasionally, you may end up with 100.2 even, or 99.8, but rarely will you get beyond that either side. Okay, questions on that guy? All right, here is our last one. So potassium is 39.1, manganese 54.9. And oxygen is 16. And I forgot to do my inventories. I got carried away here. So I've got one of these, I've got one of these, and I have 4 of these. All right, so I add those together. And Ended up with 158. So I'm going to take these and divide by my whole. And I multiply by 100. .7% in whatever element is my part. $34.7 and go back, add these up together. And I ended up this time at a 99.9. But we're going to safely assume that we're where we need to be. Okay? Questions on that? All right, get your Chromebooks out.